Hello everyone, I'm Khurram Soomro and I'm presenting our work from ICCV 2017 called Unsupervised Action Discovery and Localization in Videos. This work is co-authored with Dr. Mubarak Shah. So the motivation behind this problem is that current supervised action localization methods have a set of training videos, and for that someone has to manually go through each one of those videos and assign a video class label as well as annotate the actions in each frame of that particular video by putting a bounding box. Now that kind of work is tedious, it is time consuming and could be expensive. It is impractical when the number of action classes goes to a large amount and the videos become of a longer duration. Also, because humans are annotating these videos, it could lead to unwanted biases and errors. To avoid these kind of challenges, we propose an unsupervised action localization approach. So in our paper, we present a novel approach that addresses three sub-problems. So first, given a set of videos and the number of actions, we would like to discover actions by clustering them in the training set of the videos. Next, we would like to annotate these actions in the training videos. And lastly, once we have the video class labels as well as bounding box annotations, we would like to perform action localization in testing videos. So the proposed approach looks like this. So we have a set of videos where we have multiple action classes, multiple actions, and no video labels and no annotations. And the output of our algorithm would be video action clusters with action annotations, and then we would like to use them for performing action localization in testing videos. So first, I would like to introduce the action discovery algorithm. So it starts by having a video set, a training set, and we know the number of action classes that we want to cluster. So we start by computing low-level features for each video, and then you apply spectral clustering to get k clusters if we have, assuming that each cluster belongs to a particular action class. Once we have these k clusters from spectral clustering, we would construct an undirected graph for each one of those clusters and extract a dominant set. Now, dominant sets are known for high internal homogeneity and low inhomogeneity across for items outside the clusters. We use those dominant sets and the non-dominant set, we cluster them into one group and initialize each cluster with the dominant set. Then we perform an iterative approach where we use the dominant set from each one of those clusters to train an SVM classifier, where the dominant set is the positive examples and all the remaining videos from the non-dominant sets are negative examples. We perform this iteratively where we use the classifier to select top n videos, and each one of those videos is added to the cluster itself. This is performed in an iterative manner until we have no more videos left in the non-dominant set. Now, once we have these k clusters representing k action classes, we would like to spatiotemporally annotate the actions in those videos in the training set. And for that, we propose a knapsack approach. Now, first, I would like to define this knapsack problem. So a simple 0-1 knapsack problem, what it does is that, let's say we have a set of items and we want to put them in a bag. There's a limit to the items that we can put in the bag, which is given by the weight. Let's say it is 15 kg. Each one of those items has a particular weight assigned to it as well as a value. And the way that we want to put the items in this bag is that we want to maximize the value given the weight limit for that particular bag. We use this analogy to perform action localization and annotation in our training videos. So first we start with segmenting the videos into supervoxels. So here we have one training video and we would like to segment this using low-level features to come up with these fine action contour segments. Once we have that, then we define a value and a weight for each one of those supervoxels. Now this value tells us the action distinctness score of a particular supervoxel belonging to the foreground action. And the weight is the volume of that particular supervoxel in a video. Now once we have the knapsack value and weight, we construct a directed acyclic graph using these supervoxels, where nodes are supervoxels and edges are between spatiotemporal neighbors. Now once we have this graph, we apply knapsack optimization. However, we apply some temporal constraints because we want one contiguous segment to be selected for that particular action. We don't want to select discontinuous groups of supervoxels from this video, and that will lead to like action broken into several parts. So you want to combine them together so that you have one contiguous action, such that shown over here. And once we have this, we perform this process iteratively to get multiple annotations from our training set of videos. Once we have this iterative process performed, this will give us a set of annotations as shown by the action contour in the video. Now, first I would like to define the knapsack value. So given any video, we would like to define a knapsack value for all the supervoxels present in that particular video. So the formulation looks something like this, where it consists of three parts. First is humanness. So for computing the humanness of each supervoxel, we detect human bounding boxes in each frame of the video. And we look at how well those bounding boxes overlap with the supervoxels in that particular video. So the good overlap and high detection score would give us good humanness score for each one of those supervoxels. Our second component is the saliency. So we apply a saliency method that gives us the most salient region of the frame in this video at a pixel level, where the red score shows that it is highly salient as compared to the blue ones in the background. And finally, we use motion boundary that tells us what parts of this video have high motion and could belong to an action. Now, once we've defined the knapsack value, we defined the total weight of a knapsack. And the way that we do that is we accumulate the average bounding box size in each frame to give us the approximate volume that an action would contain in that particular video. So that's shown over here. So this will give us the value and as well as the weight of this knapsack. Once we have this, then we construct a directed acyclic graph, such as shown over here. Now here, each node is a supervoxel, and directed edges are between spatiotemporal neighbors. Now, apart from each supervoxel being represented by a node, we have two dummy nodes added to this graph, which is a source as well as a sink. Now, the way that we connect these nodes in this graph is that we connect the source node with all the supervoxels present in the first frame of the video. Here we are assuming that the video is trimmed, and such that the action starts from the start of the video until the end of the video. And the sink connects to all the supervoxels present in the last frame of the video. Now, for all the nodes that are between, that lie somewhere in the video, we connect them such that they have a temporal overlap between these supervoxels, as shown over here. Now, once we define this adjacency matrix, then we impose some temporal constraints, shown by this formulation. Now, these temporal constraints, what it does is that it wants to ensure that we select one contiguous action in this entire video, from the start until the end of the video. And the way that we do that is that we make sure that a node is only selected if it's one of the temporal predecessors is also selected. So for example, if you look at the last row of this temporal constraint, it says that the supervoxel node 7 should only be selected if either 5 or 6 is selected. And we impose this by making sure that the sum of each row constraint is less than or equal to 0. Now, once you have this, then we introduce the knapsack formulation given by the binary integer linear program, shown over here, where each supervoxel node in the graph is represented by u, the knapsack value is represented by pi, and the knapsack weight is represented by theta. Here we want to maximize the value of the item selected in the knapsack, subject to the total weight given by the theta here. So here, if you have the graph as shown over here, we select a set of nodes that belong to the action that give us a final action annotation. Now, once we have these annotations, and since I mentioned earlier that we do this in an iterative manner such that we have multiple annotations in each videos, we want to use these video level labels as well as the annotations to train an action detector. However, some of these action annotations could be for people who are in the background and could be false positives. To ensure that we select good annotations, we propose another step where we want to jointly select these annotations. So let's say we have multiple annotations in each video of a cluster. we propose a binary integer quadratic programming where we compute the distance matrix between each one of those annotations in a set of cluster videos. And we want to minimize this such that we want to select one video, one annotation from each video. And that will ensure that we have the most similar annotations across a group of videos within a cluster that belong to the same action class. Now, after we have the final good annotations as well as the video level labels for each one of those training videos, we want to learn action classifiers. Now, earlier I mentioned that our knapsack value consisted of three components, which was humanness, saliency, and motion boundary. However, all of these components depend on low-level features. So none of them have been learned discriminatively. So what we do here is we use the features for each one of the supervoxels to learn an SVM. That tells us if that supervoxel belonged to any one of those annotations, we can use that to compute a score when we are applying knapsack in our testing videos. Apart from learning a unary score for each supervoxel using SVM, we also look at the pairwise relations of the supervoxels. Now, these pairwise relations could be supervoxels that both belong to the foreground, one of them belongs to the background, or both belong to the background. And here's the structural SVM formulation, where we look at a pair of supervoxel nodes and use that to learn a pairwise relationship, where we assign a different label based on whether both belong to the background, one of them belongs to the foreground, or both of them belong to the foreground. And here is the loss function for that structural SVM formulation. This ensures that we look at the right pairs in our training and testing videos. Now, once we have learned this action classifiers, we update our knapsack value. So now, instead of having three components, we have five components. So first was the humanness, saliency, and motion boundary. However, after using the annotations, now we have introduced a unary score for each supervoxel, as well as a structural SVM-based pairwise score. Now, once we have this, then we can perform unsupervised action localization. So for our experiments for action discovery, we do that for 5 data sets. So we have UCF Sports, JHMDB, sub-JHMDB, Thomas 13, and UCF 101. And we perform action localization on 4 data sets, as shown over here. For our experimental setup, we extract features that are 3D, deep learning features, as well as IDTF. Our evaluation metrics are for action discovery is percentage of clustering accuracy. And for action localization, we use the standard metrics, which is the ROC and AUC curve at multiple overlapping threshold with the ground truth. First, we show the results for our unsupervised action discovery approach. So here, we compare our proposed approach with some known methods for clustering, such as k-means, k-medoids, n-cuts, dominant sets, spectral clustering, as well as the state-of-the-art dual assignment k-means. And here we show our results as compared to all of these methods on UCF Sports, where we've used IDTF as well as C3D features. One thing to notice here is that C3D gives us better results as compared to IDTF because it has good distinguishing features that helps us in better clustering. Our next results are on sub-JHMDB. Then we have JHMDB, Thomas 13, and finally UCF 101, which has 101 classes. And all of these we perform better than the existing state-of-the-art and known clustering algorithms. Next, we want to look at how well we have annotated these actions in our training videos. So here we propose a weakly supervised action localization approach. So what we say is that, let's say we assume we have perfect video class labels. We just want to look at the performance of our annotation to see how well we can localize these actions in testing videos. So here we are showing the results on UCF Sports. We compare to existing weakly supervised approach and show results on the first 5 actions on UCF Sports, and here the next 5 actions. And on average, we perform about 6% better than this weakly supervised approach. So next, we want to show the unsupervised action localization results on each one of those data sets. Here, I'm showing our results using shown by the yellow action contour, and we compare that with the ground truth shown by the green bounding box. Now, as you can see, Using our temporal constraints, as well as using supervoxel, we are able to get fine contour and one continuous segment of an action for the entire video. Here are some more results on sub-JHMDB. Here's JHMDB, which has about 21 actions and about 900 videos. And finally, we show results on 2MOS13, which is one of the largest data sets for action localization, with 24 actions and about 3,000 videos. And as you can see, we can localize it pretty well. Now, we want to show the quantitative results. However, since we are the first to propose this unsupervised action localization, we compare our method with the existing supervised action localization approaches. So first we show results on UCF Sports, where our results are shown by the red curve, and all the remaining state-of-the-art methods are shown by different colors. So here, as you can observe, we perform competitive to the state-of-the-art results. And in some cases, we even perform better than some of the supervised approaches and supervised baseline shown by the black curve over here. Here are some more results on sub-JHMDB. So here we perform a proposed method is shown by red curve, and we perform better than the supervised baseline for action localization. Here are results on JHMDB, which has about 21 actions, and we perform significantly better than a supervised baseline approach and close enough to the state-of-the-art supervised methods. And finally, on 2MOS13, showing our localization performance on different overlapping thresholds. Right. Now, since our method had different components to it, we want to analyze how each one of those contributed to the final performance. So first, we would like to see when we used a joint annotation selection using the quadratic programming approach, we show that we significantly improve the performance by selecting good annotations to train our action detector to perform action localization. Next, we would like to show the contribution of each one of the components in knapsack value. So our knapsack value consisted of humanness, saliency, motion boundary, and then we also added two more components, which is the unity value from SVM and the pairwise from the structural SVM. And here you can see each one of them contributes, and in combination we get a significant boost. If you want to look at individual performance, we show that the pairwise from structural SVM gives the best performance individually for knapsack value. So in conclusion, we addressed a new problem for unsupervised action localization by performing automatic discovery of action class labels using dominant sets. We propose a novel knapsack approach for annotating actions and localizing them in action videos. We also propose a quadratic programming approach that jointly selects these annotations to get better final annotation results. And finally, we use structural SVM to learn pairwise relations that helps us in giving better knapsack value and better localization. Thank you.